Dear friends, Mass Aspirants groups organizes online problem-solving sessions to help the students who prepare for different national level competitive examinations like IIT, JAM, CSER, NBHM, etc. As a part of that series, today we have a session on integral calculus, and we have Mr. Krishna Kanta Misra from Assam is with us. Mr. Krishna studied his M.Sc from Cotton University, Guwahati, Assam, and now enrolled for M.Tech course in IIT Kanpur. I hope that today's session on integral calculus will be really helpful for you in your preparations for exams like IIT JAM, etc. I would like to express my sincere thanks and gratitude to Mr. Krishna for accepting our invitation and joining with us. Mr. Krishna qualified GATE examination with All India rank 25 last year, and I'm sure that he will be the right person to share you some preparation tips and tricks to clear this type of exams. So I welcome everyone to this program. Welcome, Krishna.
Thank you very much for the nice introduction. And most importantly, sir, thank you so much for giving me this opportunity to, to serve the people. It's been like one of my deep wishes to teach students, to share mathematics with students. And so I never thought I would be able to get this opportunity to serve this kind of thing. So there's not much to say about it because Sari pretty much said everything. I think we can start the session now. So because it's a session on integral calculus, so I picked something that is from which questions are asked. So the first thing that I chose is a Riemann sum. And we are all familiar with what Riemann sums are, right? So Riemann sum is nothing but an expression of this form that you can see in the picture, point number 2. Sorry, Riemann sums. For any function f defined on a closed interval area, partition P of a into a collection of subintervals, x out, x1 up to like that, all these things, then maybe I'll just explain the picture itself. So suppose you have a closed interval area, A is here, B is here, and you partition it into with finitely many points. I'll call A to be x0, x1, x2 up to xn, b. Then we have all these subintervals like x0, x1, x1, x2, like that, up to xn minus 1, xn, where xn equal to b. Then what we do is we take 1 point from each subinterval, x0, x1, x2, x1, x2, and so forth up to xn minus 1, x minus 1, xn. Then we take the function values at each of these points, and then we multiply by the lengths of all these subintervals. So what we get is we get an expression like this. If we take the sum of all the function values and the length of each subinterval, we get an expression like this. Okay. And these xi's here are from each subinterval. When we take the sum, there is something called the Riemann sum, and that corresponds to the partition P that we have chosen. All right. And geometrically or physically, the meaning of Riemann sum is nothing but the sum of the areas of the rectangles that you have corresponding to a partition. That is it. That is our Riemann sum. And see, when computing the Riemann sum, we chose our curve as well. Like this was determined by the curve that we have. The next point to note is something called, sometimes we call it the norm of the partition P. And by norm, we mean the maximum of all the lengths of the subintervals. See, we had the subintervals, right? X0, x1, x1, x2, up to x minus 1, xn. Each of these subintervals have a certain length. The maximum of all their lengths is said to be the norm of the partition P. Okay. So once we know what a norm is, we can define what the integral of f over the interval AB is. That is defined by this expression. The integral of f over AB is nothing but the limit of all the Riemann sums. This is the Riemann sum. And the limit of all the Riemann sums as the norm of P goes to 0. That is defined to be the integral of f over AB. So that is what we have. The connection between Riemann sums and the integral. Do you guys have any question so far? Okay, no question. So, hoping that you know what the Riemann sum and what the Riemann, how it connects to the integral is, let's try to solve this question. The first question I've chosen, it was asked in Mathematical Statistics of JAM 2019. So, let's try to solve what this is. Limit of n goes to infinity, and the expression is n plus 1 plus 2 by n plus 2 plus 2 by n plus n over n root n. So when you see a sequence like this, or rather a sum like this, our aim is to to realize this as a Riemann sum. As for example, we can do something like this. This n, we can pull it outside, and I can write this as 1 plus 1 by n plus 1 plus 2 by n plus 1 plus n by n. So I can further improve on this by writing 1 plus 1 by n into 1 by n plus 1 plus 2 by n into 1 by n plus 1 plus n by n into 1 by n. So now if you look carefully, there is a certain pattern here. So it looks like, if you look at this expression here, this one here, you will see that there is a certain function, like say fx is equal to square root of 1 plus x. It looks like this function is assuming the values at the point 1 by n, at the point 2 by n, at the point n by n, right? So these are the values of the function at the point 1 by n. This is the value of the function at the point 2 by n. Likewise, this is the value of the function at the point n by n. And then it's nothing but 1. And at the same time, it's multiplied by the term 1 by n in its case. 1 by n, 1 by n, 1 by n. So if you compare to this expression, it's nothing but a Riemann sum, right? So we have realized this as a Riemann sum actually. So it's like we have an interval 0, 1 by n, 2 by n, 3 by n, like that, up to n by n, this is nothing but 1. And so it's a uniform partition. By uniform partition, I mean each of the lengths of these subintervals are all the same. They are all 1 by n. They're all 1 by n. Guys, is it clear to you all what I'm explaining so far? You can please say either a yes or no, because if it's a no, I can explain from the start.
Yes.
Is it clear?
Yes, sir.
Yes, sir.
Okay. So, so you can see that it's a Riemann sum now, right? Now, if you see this 1 by n is the norm of this partition, because it's a uniform norm where the length of each subinterval is 1 by n. So 1 by n is nothing but the norm of p. That is the norm of p. And this norm of p goes to 0 as n goes to infinity, right? So if you want to take the limit of this sum, n plus 1, n plus 2, up to n plus n, up to n root over n root n, this is nothing but the integral of a certain function. What was the function that we chose? I mean, that we had. It's nothing but square root of 1 plus x dx. Now, the tricky part here is what are the limits of this integral? So to find the limit, just look at the first point of the partition, 1 by n, right? Now, as n goes to 0, 1 by n goes to, as n goes to infinity, 1 by n goes to 0, as n goes to infinity. This is the first point of the partition. So our lower limit will be 0. And the last point in the partition, we chose it to be n by n, that is nothing but 1. And as n goes to infinity, this goes to, and this remains as 1 itself, as n goes to infinity. So it's nothing but integral of the function square root of 1 plus x over 0 to 1. Let me just remove this. And if you integrate this by parts, you get, no, you don't have to integrate by parts, you just have to use this formula, 1 plus x equal half plus 1, 2 by 2, 3 by 2, x plus 1, 0 to 1. So this will be 2 by 3, 2 by 3 by 2, minus 1. So it is nothing but 2 by 3, square root of 8 is 2 by 3, minus 1. So that is your answer. Maybe they ask us to compute, to round off the answer to 2 decimal places. That one you can do easily. This will be given an on-screen calculator, right, in the exam. Is it clear, guys? How we have arrived at the solution? Guys, is it clear?
Yes, sir.
Okay, great. Then let's move to the next problem. It was again asked in 2021 in the paper Mathematical Statistics. I chose these problems from Mathematical Statistics because sir asked me to choose problems from this one as well, because there are students from statistics, and that's right, to reach out to them as well. Now see here, the expression is 1 plus 1 by n let me test. Right, and this whole thing to the power 1 by n, and we are asked to find the limit of this. So let us start by assuming that the limit exists. So I'll set the limit to be equal to L. Suppose L is equal to, defined by the limit of this. If the limit doesn't exist, then as we go on solving the problem, we will face some difficulties. But if we don't face any difficulty, and if we indeed can compute what L is by this assumption, then that means our assumption that the limit exists is correct. Now note in the previous problem, while computing this,
Krishna,
yes,
excuse me, please keep your mic a little bit closer so that your voice will become more clear.
okay, so is it better now?
Yeah, Yes.
Okay. So note that when you are finding the limit of this, okay, not here, but here. There was something 1 by n, which was nothing but the length of the subinterval, right? And then there was a pattern of the function values. So we will try to do the same. Like we'll try to realize this particular quantity here as a Riemann sum too. But at the moment, our 1 by n is flying up here. So as usual, what we do is we take the log of L. And if I take the log on the right hand side too, I can interchange the log and the limit because log is a continuous function. Log of Is it clear, guys? Am I audible, guys?
Yes, sir.
Yes.
Okay.
Yes, sir.
Yeah.
Yes, sir.
Yes, sir. You are acceptable for me.
Okay. So limit is we take the log and the limit, right? So when I take the log, this 1 by n will come down here, and by property of log, it's 1 plus 1 by n, log of 1 plus 2 by n plus log of 1 plus n by n. And it is nothing. This is limit as n goes to infinity. Log of 1 plus 1 by n into 1 by n plus log of 1 plus 2 by n into 1 by n again. Go on. And log of 1 plus n by n into 1 by n again. So like before, you see that there is a certain pattern here. Log 1 plus 1 by n, log 1 plus 2 by n, dot dot dot, log 1 plus n by n. So what is the function? It looks like all these things look like this is a certain function fx, which is log of 1 plus x, and it is assuming the values at the point 1 by n, 2 by n, 3 by n, like that up to n by n is equal to 1, right? All these things, if you look carefully, that is nothing but the function log of 1 plus x. And at the same time, I multiply it with the factor 1 by n in each case, which is nothing but the length of the subinterval for the partition that we have. So again, just 0, 1 by n, 2 by n, and n by n equal to 1, right? So the first one we chose is 1 by n, the last one is n by n. So what we have done is we have just realized this whole thing as a Riemann sum, and then we are taking the limit of as n goes to infinity. Thus, it is nothing but the integration of the function that we have log 1 plus x. So this whole thing is equal to integration of log 1 plus x dx. And what are the limits? That is the question. What are the limits? The first one that I chose was 1 by n, and as n goes to infinity, this goes to 0. The last point is n by n. There's nothing but 1. So as n goes to infinity, it remains as 1 itself. So the limits are 0 and 1. And if you integrate it by parts, there's a routine competition. You'll get this to be log 4 by 8. You can check. It is quite easy to check. All right. So this log 4 by e is nothing but or log l, because that is what we started in the first place. Log l is equal to log 4 by e. And because log is a 1-1 function, we are forced to be sure that L is equal to 4 by A. That is the whole limit, or limit of whatever expression that we had. It is nothing but 4 by A. So the correct option is option D. D is the correct option. Is it clear, guys? Do you have any doubt? Like, we arrived at a solution. If you have any doubt, you can just ask me. Any doubt, guys?
Am I audible? Hello,
Yeah.
sir.
Yeah, you're welcome. Please ask.
Function is defined by limit n tends to infinity, 1 plus 1 upon n, and all. And the third step is not third step, precisely fourth step. What is
I mean,
what you do?
this one you mean?
No. The fourth step, you are multiplying 1 upon n to the like domain of that logarithmic function. So it's not actually multiplicated to domain. It's just a factor multiplication with the logarithmic function, right?
Yeah. You are multiplying 1 by n to the log of 1 plus 1 by n. Like,
Yes. So log 1 plus 1 upon n, it's a whole, and multiplying by 1. Yeah. Okay.
okay. Yeah, maybe I can rewrite this actually to so that you don't get confused. I'll rewrite it. So this is actually limit n goes infinity. I'll just write the 1 by n in the first, so that you don't get confused. 1 plus 1 by n plus 1 by n into log of 1 plus 2 by n plus dot. So 1 by n into log of 1 plus n by n. Is it clear now? Is it better now?
It is. It is.
Okay. So yeah. Any question? Okay. So the main point is that we try to, when you look at an expression like this, like limit 1 plus 1 by n, whenever you see something like 1 by n is there, and there's a certain consistent pattern of 1 by n, 2 by n, n by n, then always try to realize that as a Riemann sum, and then try to find the limit by considering the integral of the function. That is how we solve such problems. Do you see the similarity between the first and the second problem? There is a 1 by n, and there are 1 by n, 2 by n consistently, right? And that is how we solve it. Clear? Okay. So there's a small homework for you so that you understand what is really going on. The question is, find the limit as n goes to infinity of sine pi by 2n, sine 2 pi by 2n, sine n minus 1 pi by n. And the whole thing is raised to the power 1 by n. So I'll just give you a hint orally. So just like the last problem, the 1 by n was flying up here, right? So just try to bring it down to the ground by taking the logarithm and all. And there will be some kind of integration, all those things. Then when you solve the problem, you will encounter this expression, integration of log sine x dx from 0 to pi by 2. The value of that is actually minus pi by 2 log 2. There's a long solution. If you studied NCERT textbook in class 12, there was this problem, this very problem. Okay, so it's a long solution. So I just gave the value here itself so that you don't face difficulty. Use this value and prove that this limit exists, and it is actually it has the value 1 by 4. That is your answer. I urge you to try it so that you understand how we find the limit by using Riemann sums. Okay. Okay, so that was about Riemann sums. Because we have a lot of topics to cover, I'm choosing maybe at most 2-3 problems from each topic so that we can have a wide coverage. So the next topic that comes in our line is surface areas and volumes. So the long story short, consider any surface in 3 dimensions. I'll use a surface. I denote it by S, and we assume that the surface S is expressible as a function of x and y. That is because we usually take z to be the dependent variable and x and y to be our independent variable. Then we have something called surface integral. So if we have a function f of x, y, and z, which is defined on the surface S, where S is given by z as a function of x and y, then the double integral of the function over the surface S is defined by this expression. So note that we were finding the double integral over the surface S. Now we have changed it to D. So what is this D? D is nothing but the projection of this surface S on the xy plane. If you project the surface S, we assume that we get a certain planar surface D. So D is actually a planar surface. D is a planar surface on the xy plane. Planar surface on the xy plane. So when we have something like this, the double integral of f over the surface S is nothing but the same double integral. You replace z by the function in x and y, z, x, y, and then you multiply this by this quantity. 1 plus the partial derivative of z with respect to x, whole thing squared, plus the partial derivative of z with respect to y, whole thing squared, dx, dy, and you integrate over the planar surface D, which is the projection. Okay, and this is how we compute the surface integral of any function over the surface S. Now we can ask, what is the surface area of S, right? Now see, when we think about surface area, the surface could be any curved surface in the 3 dimensions. It could be the surface of a cylinder, it could be the surface of a cone, it could be the surface of a sphere and all. We can still compute the curved surface of all those, the surface area of all those curved surfaces by using this formula. Just substitute 1 in place of this. So the surface area is nothing but the double integral of 1 over ds, and like usual, you just get, if you project the surface S on the xy plane, you get a D, and just find the double integral. This is coming from this equation. Is it clear, guys? How we find a surface area? Guys, if you have any question, you can ask. That is all okay. That is fine. Any question, guys, regarding how we find surface area and surface integral?
No, sir.
Okay. Then we'll just start with the next problem. So the next problem is, it was asked in Maths, Jan 2023. For each t belonging to 0, 1, the surface PT is defined by this. Let AT be the surface integral of PT. Then what is AT? Surface area of PT. So PT or PT is nothing but x, y, z, such that x square plus y square into z is equal to 1, and x square plus y square lies between t squared and 1. So we are parameterizing it by t, right? There's a t here. So see, from this part you can see z as a function of x and y like this. Z is equal to 1 by x squared plus y squared. And from here you can see the projection of the surface on the xy plane. It is nothing but the disk. This gives us a disk, punctured disk, right? Or rather a hollow disk. X squared y squared lying between t squared and 1 squared. So it's nothing but something like this. So this is t, and this whole thing is 1. So we are considering this one, this region. This is the d we have. But by d I mean this projection of the surface S on the xy plane. So now by small at is a surface area of PT, and by formula our formula was this one. The surface area is this. There's nothing but the double integral over d square root of 1 plus del z del x all things squared plus del z del y all things squared over dx dy, and integrate over d. Or d is this. And that is nothing but if we compute zx, so z was this one. So what is zx? So zx is nothing but minus of 2x by x squared plus y squared whole square minus of 2y by x squared plus y squared whole square. If you substitute all these things in this expression, then you get d is 1 plus 4x squared by x squared plus y squared put into 4 plus 4y squared by 1 x squared plus y squared whole into 4 dx dy, and d I can replace this d by what they actually gave us. D is x squared plus y squared lying between 1 and t squared. So this is nothing but our AT, the surface area of S. So I think if you look up the other option, it will be option A, right? It is in option B, x squared plus y squared holding squared, but that is not correct. We got power 4. So option A is correct. Now it is an MSQ. There is yet another part that we have to check. We have to check whether the limit exists, whether this limit exists or not. Limit of at t as t equals to 0 from the positive exists or not. Exists or doesn't exist. Here's our question. To do that, what we do is we first find the value of this actually. We just compute this surface area, the actual surface area. So how do we do this? X squared plus y squared lying between t squared and 1 plus 4 so plus y squared plus y squared whole thing to the power 4 dx dy, and we'll get 1 plus 4 by x squared plus y squared 3 dx dy between 1 and t squared. This is our AT. Now when you arrive at say the D, this describes this determines this region D, right? It's like a hollow disk between two circles of radius d and 1. So when you have something like this usually, and when you have the terms like x squared plus y squared involved, and when you have regions like disk and all those things, then usually the easiest way to compute such surface integrals is by changing it into polar coordinates. So to compute this integral, we just set x equal to r cos theta, y equal to r sin theta, so that x squared plus y squared is equal to r squared, and dx dy, this unit, like dx dy, this becomes r d theta dr. I'll explain how it comes. Like there is something called change of variables in the later part of this session. I'll explain how it comes. For now, we can just take it for granted that dx dy is equal to r d theta dr. So in that case, what happens is this expression is exactly equal to square root of 1 plus 4 by, it will be r squared to the power 3, r6 into r d theta dr. Now our r was, see, our r was between t and 1, right? It starts from t, the radius, and it goes till 1. So the radius r goes from t up to 1, and theta goes from 0 up to 2 pi. It's like a complete rotation from 0 to 2 pi. Because there is no theta involved here, I can just separate these two integrals, and I'll just get a 2 pi outside. I'll just make it short. 2 pi integration of 1 plus 4 by r plus 6 into r dr. R goes from t to 1. So to check whether the limit, this limit, limit at t as t equals to 0 from the positive side, it's the same as checking whether this integral exists or not. This is an improper integral now, right? 1 plus 4 by r plus 6 into r dr. So we just have to check whether this integral exists or not. Guys, are you all following so far what I'm trying to explain? Please talk to me so that I know whether you are following or not.
Yes, sir.
No doubt so far?
No, sir.
Okay. So, the problem now is to check whether this improper integral, converges or not. That is our problem. So that those kind of things we usually study in analysis, right? So this is our improper integral now. If you note, you will see that this expression r into 1 plus 4 by r plus 6, it is actually greater than r times of 4 by r plus 6, because there is a 1 here, there is no 1, so it is this, and that is exactly equal to 2 by r squared. And if you try to integrate this one, 2 by r squared over dr between 0 and 1, this is divergent. You can check. Okay, 2 by r squared is nothing but minus 2 by r. You'll get this is equal to minus 2 by r, all goes from 0 to 1. And this limit, as r goes to 0, it doesn't exist because r is in the denominator here. So this is divergent. Since the integral of this is divergent, so the integral of this has to be divergent. So if it is divergent, that means this is divergent, and so this limit doesn't exist. Therefore, the limit of f as p goes to 0 from positive doesn't exist. Guys, is it clear now how we have found out that the limit doesn't exist?
Yes, sir.
Yes, sir.
Okay, so our correct options are option A and option C. The limit doesn't exist. So we can move to the next problem. I've drawn the diagrams and everything so that we can save a lot of time when we solve such questions. let S be the part of the cone, z squared equals x squared plus y squared between the planes z equal to 0 and z equal to 1. Then the value of the surface integral, blah, 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 is what? So these are cone. Okay, this is our cone, z squared equals x squared plus y squared. Here's something that I want to say. When you usually compute surface area and surface integrals, it's usually good to know how the surfaces look like, because when we know how the surfaces look like, we can easily compute the integrals and all by setting the correct limits. So it's a good practice to have an idea about how the surfaces look like. So our cone z squared equal to x squared plus y squared, it looks like this, like how I've shown. And S is part of this cone between the planes z equals 0 and z equal to 1. So z equal to 0 is nothing but the xy plane, is z equal to 0. And z equal to 1, I've drawn here, z equal to 1. So if you cut it off, you get this cone itself. And we want to find the surface integral x squared plus y squared ds over s. So finding surface integral means, it means nothing but integrating this function over the entire surface s. And while doing that, you'll have certain factors like square root of 1 plus zx squared plus del z del y squared. All those things will come up. Yeah, okay. So our z squared here is x squared plus y squared. So z is nothing but, before I do this, maybe I can do this later on. You know, just write what this should be. So this surface area will be x squared plus y squared into 1 plus zx, the partial derivative with respect to x, plus zy, the partial derivative with respect to y, whole thing squared, dx dy over the planar surface D. What is D? Our D is this one, the projection of the cone on the xy plane. Now, because a cone, if you project it, you'll get a perfect circle on xy plane. That is like easy to visualize. We all know what a cone looks like. Now, the tricky part here is we get a disk, not a circle. We get a disk. The tricky part here is what will be the radius of this disk, because we are going to need the radius of that disk while computing this double integral. I'll tell you how it's done, but first let me just compute what zx and zy are. Zx is nothing but x squared, sorry, or z is z squared is x squared plus y squared, so z is square root of that. So zx will be xy squared of x squared plus y squared. Zy will be y squared of x squared plus y squared. So this whole expression, this is nothing but this is equal to x squared plus y squared square root of it will be 1 plus it will be another 1 dx dy, and with the surface planar surface D. So square root of this square root 2, I pull it out. We get this dx dy over D. So, like before, see that this, so we get a nice disk. D is a nice disk, and we get an expression like this, x squared plus y squared. So again, we use polar coordinates, x equal to r cos theta, y equal to r sin theta, and x squared plus y squared becomes r squared. So when we substitute this one will be square root of 2 r squared into dx dy is nothing but r d theta dr. Now r goes from where to where? Theta goes from where to where? So see, I told you that this is a disk D. Now this is where the radius of the disk comes in, because we want to put the limits for r. This r stands it's like the radius vector, right? The magnitude of the radius vector. to find out the radius, what we do is we look at the value of the z, the limit. Z equals 0 and z equal to 1. So if you substitute z equal to 1, you get x squared plus y squared equal to 1. Right? So substituting z equal to 1 gives us this circle. And if you notice, the radius of this disk is exactly the same as the radius of this circle. So if you substitute z equal to 1 in the equation of the cone, you get x squared plus y squared equal to 1. And that is nothing but a circle of radius 1. Radius 1. So if you project it on the xy plane, you get a disk of radius 1. So r will go from 0 to 1, theta goes from 0 to twice y, because it's a full disk, not a hollow disk. It's very easy to compute, and I urge you guys to try and check that there's nothing but pi by root 2. Actually, I tried myself because I was preparing for this section. So the answer is pi by root 2. The option B. The answer is option B. Is it clear, guys, how we computed this surface integral? Or am I being too fast? Would you like me to slow down, or is it good the way I'm doing it?
It's fine, sir.
Are you guys following everything, whatever I'm trying to explain?
Yes, sir.
Okay, so the answer is pi by root 2. The next problem is we are asked to find, okay, let's see what the question is. The area of part of the surface of paraboloid x squared plus y squared plus z equal to 8 lying inside the cylinder x squared plus y squared equal to 4 is what? So like before, it's a good idea to know what surface or what they look like. So the paraboloid is given to be x squared plus y squared plus z equal to 8. So you can write z as 8 minus x squared minus y squared. Now try to convince yourself that this paraboloid looks like this, what I have drawn here. Okay. This looks like this. Like there will be surface. I haven't drawn, like I haven't made things like this so that it's clean, but actually it's a surface. Now we want to find the area of the part of the surface lying inside the cylinder x squared plus y squared equal to 4. So this again we are given a cylinder x squared plus y squared equal to 4. A cylinder looks like a circle in xy plane, but if you extend it by making parallel to the z-axis, it has something like this. This is our cylinder. Okay. So the surface inside the cylinder is exactly this. We are asked to find the surface area of this paraboloid. So again, it's easy. We have z to be this. So the surface area is nothing but integrate the function 1 over ds. Over the entire surface S that we are trying to consider. This is our S. So there is nothing but square root of 1 plus zx whole thing squared plus zy whole thing squared dx dy d. Now d is nothing but the projection of this surface on the xy plane. So because we have a cylinder, the projection is easily this one, right? This is very easy to check that one. So our d, this is our d. Again, it's a disk. Now the disk has radius 4 because our cylinder was given by this expression x squared plus y squared equal to 4. Sorry, it has radius 2 because our cylinder was given by this expression x squared plus y squared equal to 4. Z is nothing but this. So zx will be minus 2x. Minus 2x, zy will be minus 2y. So this is nothing but 1 plus 4 x squared plus y squared. I'll just factor the 4 out. Dx dy over d Again, use the polar coordinates, x equal to r cos theta, y equal to r sin theta, then you'll get 1 plus 4r squared r dr d theta. Now here's a word of caution. Whenever you use this kind of polar coordinates, make sure that dx dy is replaced by r d theta dr. Usually we forget to include this r when we replace dx dy. So don't forget this r when you replace dx dy. Okay, r dr d theta. So the limits of r are from 0 to 2, and I mean the radius goes from 0 to 2 because our cylinder looks like this, x squared plus y squared equal to 4. Theta goes from 0 to twice pi. Again, it's easy and just some mechanical job, and you find that the answer is actually equal to pi by 6, 17, 3 by 2 minus 1. So there is nothing but option C, pi by 6, 17, 3 by 2 minus 1. Option C. Guys, I'm skipping the steps so that it doesn't consume much time, so we can cover lots of problems instead of just working on all these routine computations. Is it clear, guys? The solution?
Yes, sir.
Any doubt in this problem or in the last problem that we have? Do you have any doubts?
No.
Okay, then let's move to the next problem. It was asked in GATE Mathematics 2022, last year. The surface area of the paraboloid between the planes z equals 0 and z equals 1 is this, round off to one surface. So the paraboloid looks like this. So this is our paraboloid. Z equals x squared plus y squared. It's always a good idea to know how a surface looks like. And between the planes z equals to 0, this is our xy plane, z equals to 0, and z equals to 1 is this. If you cut off, you get this paraboloid. Now again, if you project this paraboloid on the xy plane, you'll get a disk, right? You get a disk, and the disk has radius 4. If you check, you'll find that the disk is nothing but a projection of this part of the paraboloid, right? So that is given by z equal to 1. So substitute it in this expression, z equal to x squared plus y squared. So we'll get x squared plus y squared equal to 1. So this disk has radius 1. Radius 1. So the surface area, okay, our Z is, surface area is integral of the S over S over D 1 plus Zx squared plus Zy squared dx dy. What is our Zx? Zx is nothing but 2x, Zy is nothing but twice y. So it's all very routine again. Square root of 1 plus 4 x squared plus y squared dx dy over d 1 plus 4r squared dr goes from 0 to 1, theta goes from 0 to twice pi. So because there is no, because the limits are constants, 0 to 1, 0 to twice pi, I can just separate them. D theta, r dr d theta. Sorry, there should be an r dr d theta. Should be r dr d theta. Because these limits are constants, 0, 1, 0, twice pi, I can separate them. Integral d theta, theta goes from 0 to twice pi into integration of 1 plus 4r squared r dr. Goes from 0 to 1. We can write like this, so it will be nothing but twice pi times of this integral. 1 plus, this is very easy to compute. It's a routine computation again, and and the answer is actually equal to 5 by 6, 5 square root of 5 minus 1, and that is 5.33, because we are asked to find the decimal value, right? It's 5.33. Is my voice low, or is it like clear to you all? Because sir was asking me to.
Clear.
Is it okay? So the solution is clear too, like how we got this answer. Is it clear as well, the solution of this problem?
Yes, sir.
Okay.
Yes.
Next, this was asked in GATE last year. It was asked from statistics. Again, I'm covering statistics because sir asked me to cover the statistics part. There are students from statistics here too, I think. That's why. The question is, if the line y equal to alpha x, where alpha is greater than or equal to √2, divides the area of the region R, given by blah blah blah, into two equal parts. So there is a certain area given to you, R, and you are dividing this total surface area R into two equal parts by a certain line given by y equal to alpha x, where alpha is greater than or equal to √2. Then we are asked to see what the value of alpha is. So guys, can you tell me how we can try this problem? Any idea? Because it doesn't like to solve this. We don't need much of theoretical ideas. We just need some like mathematical intuitive ideas, like how we can try this problem. So any ideas how we can attack this problem? You can just speak out, guys. Like there is no no harm in saying something that is not correct. That is all okay. That is all part of our learning. It is okay. So just please speak out. Like any idea, any suggestion, any approach that you have in your mind, how we can solve this problem.
The two areas will be equal.
Pardon?
The two areas will be equal. We can compute using integration the two areas and can equate them.
These two areas will be equal, right? Because they have to be
Yeah.
exactly half, right? Yeah. So to do that, to make sure that how to, so one good idea is to know what the total area of this thing looks like, correct? If these two should be equal, then we can do it by first finding the total area of this whatever I've shown here, and then you find this two. Clear? Guys, are you following?
Yes,
Sir.
sir.
Sir, please repeat once.
See, the question asks us, okay, let's read the question again. If the line y equal to alpha x, alpha is greater than or equal to √2. So I have drawn the line here. This is y equal to alpha x, and alpha is greater than or equal to √2. This line divides the region R. Okay, let me just write down what R is. R is just the set of all points where x lies between 0 and √y, and y lies between 0 and 2. So okay, let's see what this R looks like. X, y, where x lies between 0 and √y. Sorry, √y, right? So the x coordinate should be positive, so it should lie on the right half of the xy plane, and it should be less than or equal to √y. So the limit of x is, the upper limit of x is equal to √y, or you can write this as y equal to x squared. X to √y is the same as y to x squared. So the y to x squared looks like this, the quadratic curve, square curve. So x lies between 0 and this y equal to x squared curve. So these are y equal to x squared. This is y equal to x squared, this curve, and x lies between 0 and this. So is it clear now how the x coordinate lies between this and this?
Yes, sir. Clear.
And y lies between 0 and 2. So y lies, this is y equal to 0, the x-axis, and y equal to 2. This is y equal to 2. So this is our exact region R. Okay, this is our region R. Now we want to divide this entire region R into two equal parts by means of a line y equal to alpha x. And when we do that, we want to find out what that value of alpha is. So to do that, let's first someone suggested that these two should be equal. Yes, that is correct. So let's first find out what the area of this region is. The area of R is. The area of R is nothing but the double integral of dx dy. What are the limits of x? X goes from 0 to root y, right? X goes from 0 to root y, and y goes from 0 to 2. These are area of R. These are area of the region R. Okay. So if you compute this, again it's a routine computation, you'll get 4 root 2 by 3. This is your area of R. Now, look at this line, y equal to alpha x, and we are given that alpha is greater than or equal to root 2. Now it's I checked by myself, but you can also check. So when y equal to, see, look at this, this is y equal to 2. Consider any line which passes through this point as well, this point. Then the slope of that line is exactly root 2. Okay. So they have asked us to take the value that alpha is greater than or equal to root 2. So the line should be like either at least this one, or it should be rotated towards like anti-clockwise. It should be coming in this region. It should not go in this region like this. Is it clear? Because of our restriction here, alpha is greater than or equal to root 2. Is it clear, guys, what I'm trying to explain? Okay, I'll explain again. So this is our region R. There's one point here, right? If you find the equation of this line, this will be exactly y equal to root 2x. Now there's a line given to us, y equal to alpha x, where alpha is greater than or equal to root 2. So the line has to be either this line itself, or it should be something like this, or something like this. It should not be something like this, because it is alpha is greater than or equal to root 2. Is it clear?
Yes, sir.
Yeah. So the significance of that point is that when the line is something like this, when the line is something like this, then you get a triangle here, right? You see, that's a triangle. So it is easy to compute the area of this triangle. So this line is y equal to alpha x, and I'll consider this to be the base, and this is the height. So the area of this triangle is nothing but half, I'll call it 0 AB, half, base is OA, that is nothing but 2, height is AB. What is AB? AB is nothing but the is given by the x coordinate of the intersection of this line y equal to alpha x and y equal to 2. So y equal to alpha x, so put y equal to 2, because this was y equal to 2, right? This was y equal to 2. If you substitute y equal to 2 here, then alpha, you get it to be 2 by, if you substitute y equal to 2 here, then you get x to be 2 by alpha. So So this base is exactly equal to 2 by alpha. So our base area is 2 by alpha. So the area of the triangle is half 2 into 2 by alpha. So it is 2 by alpha. Clear? So this triangular area is 2 by alpha. And since this triangle, this line y equal to alpha x divides the entire area of the region into two equal parts, this triangular area should be exactly half of the region, half of the area of R. Do you agree? Two by alpha, the area of the triangle should be half of the area of R. The area of R was computed to be 4 root 2 by 3. This was the area of R. 4 root 2 by 3. So this will be half of 4 root 2 by 3. 2, 2, 2, 2. So alpha is exactly 3 by root 2. So that is our option A, 3 by root 2. Is it clear how we arrived at the solution?
Yes, sir.
Any doubts?
Yes.
Anyone? Anyone? How we got this solution? Guys, you can speak out. There is nothing harm in speaking out. Okay, so okay, let me just go a little bit further and say why we took alpha to be greater than equal to root 2. If if the alpha was less than root 2, then the line would have been something like this. Then in our computation of area, we'll have to compute this area first, triangular area, and the area of this region as well. But it's clear that when we have a case like this, these two will not be equal because obviously this part will dominate this part. Okay. That is just an extra note, although that wasn't part of the problem. Next topic is volumes and volume integrals. So long story short, it's like it's very much similar to the surface integral that we did. So assume that we have a solid E. E is a solid that I've drawn here, and we assume that the solid is bounded by two surfaces, z equal to z1xy and z equal to z2xy. Then so the solid E is bounded by two surfaces, and we assume that the projection of this solid on the xy plane is again this projection on the xy plane is D. D is our projection of the solid on the xy plane. Now we are interested in two things again: the volume of the solid and the volume integrals. Excuse me. So the volume of the solid E is given by volume V is equal to integration, triple integral of dV. You integrate it over the entire solid E. So usually our dV is equal to dx, dy, dz. But I write the dz first because we are given that, we are assuming that the solid is bound between two surfaces, z equal to z1xy and z equal to z2xy. So I write this is also the same as dz dx dy, right? And there is a double integral. So the innermost integral dz, you take it here, integration of dz between z equal to z1xy and z2xy, and you'll get, if you integrate this, you'll get z2xy minus z1xy. You'll get this expression. And the outer integral is now a double integral over d. D is the projection of the solid on the xy plane. So double integral of this function dx dy over d. This is a function of x and y. Clear, guys? Is
Yes,
it
sir.
is it tough or easy? Like it's easy, right? If you try to connect with surface integrals and line integrals, these are all easy, right? Okay. This is our volume. Notice that this is our volume. Volume V. Volume of the solid E. And volume integrals are also computed similarly like this. Like suppose we are given volume integrals. Suppose you are given a function in 3 variables x, y, z, and you want to integrate this function f over some volume v. Then it's nothing but integrating this function over the region E determined by this v. How we do that, let's see. It will become clear when we look at these examples. So the next problem is, let V be the volume of the region S defined by, okay, it was asked in Jan 23, mathematics. So S is given by x, y, z, such that z lies between x, y, and 4, and x squared plus y squared lies between 0 and 1. So these are solid, and like how I explained here, see, the solid is bound between two surfaces, z as a function of z1 xy, another is z as a function of xy. So here too, if you notice, so z lies between xy and 4. These are z1. This plays the role of z1. This plays the role of z2. And this one, x squared plus y squared lying between 0 and 1, it's our disk, and there is nothing but D, the projection of the solid on the xy plane. So if we want to find the volume of this, it is nothing but by our usual formula, it is dV. You want to integrate this triple integral over the entire solid determined by this x. So again, I'll write dx, dy, dz. V. I'll write the dz first because we are given a bound for z, right? So I'll bring forward this dz. Dz. Z lies between xy and 4. xy, 4, and bahar we have dx dy, and it will be this dx dy will be integrated over some region B, and B is nothing but our disk, the unit disk of the disk 1. So it will be 4 minus xy dx dy over D. And again, because D is a disk of radius 1, let's use the polar coordinates again. So we can use the polar coordinates again. X equal to r cos theta, y equal to r sin theta, and dx dy. Again, I remind you that there should be an r first and then dr d theta. Don't forget this r when you replace dx dy. If you do it, then the expression becomes r goes from 0 to 1 because it was a unit disk, right? X squared plus y squared lying between 0 and 1. It's a disk of radius 1, so r goes between 0 and 1. R goes between 0 and 1, theta lies between 0 and twice pi. And 4 minus r squared cos theta sin theta dr d theta. Sorry, it should be r again. Okay, there should be a r dr d theta. R dr d theta. Again, it's a very easy double integral. We just separate them like this. Double integral of 4r dr d theta, r going from 0 to 1, theta going from 0 to twice pi, and minus double integral of r squared cos it will be, I think, for r cubed cos theta sin theta dr d theta, r going from 0 to 1, theta going from 0 to twice pi. These are very easy to compute. It's very routine computation task, and the answer we'll get is 4 pi. So the volume V is 4 pi, and in our question we were asked to find what the value of Vy pi is. So Vy pi is nothing but 4. Answer is 4. Clear, guys, how we got this answer? Do you have any doubt at any step? Guys, if you want me to repeat, I'll repeat it. There is no problem with that one. Please tell me if you want me to repeat it.
Yes, sir.
Clear? Okay. Everyone else is clear too? Or is there anyone who has like doubt with what we tried here? If there is anyone who has any doubt, please tell me. I'll repeat it. Doubt, anyone? Okay, I assume that it is followed. So next, it was asked in GATE 2021, yeah, maths. Let V be the solid region in R3 bounded by the paraboloid y equal to x squared plus z squared and the plane y equal to 4. Then the value of this triple integral is what? Again, it's a good idea to know what a surface looks like. So because our paraboloid is y equal to x squared plus z squared, it will be a paraboloid whose axis is the y-axis. So I've drawn the paraboloid like this. So these are paraboloid. These are paraboloid. And we want to integrate a certain function over this paraboloid. Okay. Now the bound of the paraboloid is given by y equal to 4. So the plane y equal to 4, which is parallel to the xz plane, will cut off the paraboloid, and it gives us to this shaded area. This is our y equal to 4, the intersection of this paraboloid and the plane y equal to 4. Now they have set the question like this to confuse us. Usually we take the projection of the solid on the xy plane, right? This is in the xy plane, but this question it wants us like the question is such that we are not getting to project it on the xy plane, but rather we project it on the xz plane like this. That is what I have done here. And because it's a paraboloid again, the projection will be a perfect disk. And to find out the radius of the disk, again as usual, put y equal to 4 in the equation of the paraboloid. You get y plus x squared plus z squared equal to 4. So that is nothing but disk of radius 2. Radius 2. Because there is a 4 here. 4 is 2 squared. So we have this paraboloid. Now we want to integrate this function. We have to compute this triple integral over this paraboloid. So our triple integral of 15 x squared plus z squared dv over the entire paraboloid v. Right? So notice that 15 x squared plus z squared v dv is dx dy dz, right? Guys, see, if you followed the last problem, I wrote the dz first. I wrote the z first, and I took it as an inner integral, right? Here, Can you tell me which one I'll put first? Which one I'll consider to be the inner integral? The z variable or the x variable or the y variable? Can you tell me? Which variable? Pardon? Can you please repeat which variable that we are going to put as the inner integral first?
Where is it y variable?
Yeah, y variable. Because the solid is bound between the surface of the paraboloid y equal to y square x squared plus z squared and the plane y equal to 4, right? So there is a certain uh, bound given to us. So y lies between x squared plus z squared and 4. This is given to us. So although I took the z because it is usually our you know intuition to consider z as the dependent variable and x and y as a independent variable. So we wrote like this in theory, but you can replace x, y, z. You can play around like this depending on what the question is. So in this question, y is given to be between x squared plus z squared, this plane, and the this paraboloid, and the plane y equal to 4. So I'll write the y first. 15 x squared plus z squared dy. This is our inner integral. Y lies between x squared plus z squared and 4. This is it, and dx dz. And you integrate this over the projection of the solid on the xy plane. This over d. D is our solid now. This this projection on the xz plane. So I think I hope it's clear to you guys how all these things are done. So
Sir, hello, sir.
yeah. Can you please repeat what you were trying to say?
I have a question regarding the given function like y is equal to x square plus z square, right? This is we can classify like implicit or explicit on that approach. So are we bound to specify like sake of our calculation we can put it like y is a dependent variable, but you're getting me, right?
Yeah, can you please repeat? Like, can you put it in other words, like what you're trying to say? Like, I'm getting a little bit, but not exactly what you're trying to.
Suppose I will be wrong, I know that, but if we are going to like z square is equal to under root of y minus x square, so basically we are just manipulating the expression. So
Yeah. We're manipulating it. Yeah, and also manipulation, and also by looking at the question, how the nature of the question is. Like, example, we are given the solid to be this paraboloid. Given see, paraboloids can be of many types, right? One will be z x squared plus y squared. This will be a paraboloid like this in this problem, where the x like where was the paraboloid? Yeah, like this. This is our paraboloid, z equal to x squared plus y squared, where the axis is parallel to the z-axis, right? Now our paraboloid is y equal to this one, where the axis is parallel to y-axis. Like, again, we have another paraboloid where x equal to y squared plus z squared. It will be a paraboloid with the axis along the x-axis. So when you look at this paraboloid, and you are also given that you are asked to consider the region of the paraboloid between, like, cut off by the plane y equal to 4. So it's pretty much obvious to us that we have a certain bound of the values of y between
right.
that square and 4, correct?
Right.
Yeah, that's why I have chosen y to be the inner integral first, so that we have this bound y between this and this. And once we have that, we can easily compute a double integral. Is that clear now?
Yes, sir.
Okay. So we have this so far, and if we do it, then it will be this. Let me just. Yeah. So if you compute this, then d, it will be you are integrating this function. There's no y here, so I'll treat it as a constant. integrating over dy, I'll get 15 x squared plus z squared, 4 minus x squared plus z squared, and all these are functions of x and z, 2 dx dz. And see, usually we do it, see, again notice that this d is our disk, and this was of radius 2, radius 2, right? And we have all these things. So we have expressions like x squared plus z squared, x, z, all those things, and disk, and the disk. So the easiest way to compute such double integrals when we have a planar disk is to use polar coordinates, not y this time. This time it should be z equal to r sine theta. So dx dz will be r d theta dr, or whatever. This r, again I remind you, don't forget this r. So if you use a substitution, you'll get an expression like this: r going from 0 to 2, theta going to 0 twice pi, theta going from 0 to twice pi, yeah, twice pi, and 15, it will be r, I think, and 4 minus r square into r dr d theta. This is a very simple double integral, because you have all the limits, these are constants, and this is only a function of r. You'll get the answer to be 128 pi at last. I've done the computation because I was asked to prepare for the session, so I urge you to check that the answer is 128 by pi, which is nothing but option A. Clear? And everyone, how we did this volume integral? Is it clear, guys?
Yes, sir.
Yes, sir.
Yeah, so again, let me repeat. So when you compute such volume integrals, so try to find out what the inner integral is, like dx, dy, dz. So in the last problem, we chose z because we had a bound for z, right? Z was bound between x, y, and 4. So we took that to be the inner integral, and then dx, dy over d is nothing but the projection of whatever it is on the plane, on some plane given by the question. So in our question, we find this to be the d in this question. Here our d is nothing but by a horizontal projection, we get this d, and we do this whole triple integral thing. So that was how we did it. Now next problem, again it was asked in GATE, statistics again. Statistics, because I think there are some statistics students here. So D is the region between, let me write down what D is. D is given to be the region between x, y, z, such that x, y, and z all lie between 0 and 1. So that means it lies in the first octant. And also we are given another restriction, x plus y plus z should be less than or equal to 1. So the maximum value of x plus y plus z is equal to 1, right? So if you remember x plus y plus z equal to 1, this is an equation of a plane which cutoff intercepts 1 on the x, y, and z axis. Like compare it to x by a plus y by b plus z by c equal to 1. So a, b, c are all 1. So it's a plane with intercepts 1 on the x, this 1 unit, and this 1 unit on the x, y, and z axis. So there's a question of these points have all these things, coordinates like 1, 0, 0, 0, 1, 0, and 0, 0, 1 that have written here. And x, y, z are positive. So x positive means it would lie on the positive side of the yz plane. Y positive means it will lie on the positive side of the xz plane, and z positive means it will lie on the positive side of the xy plane. So the solid that you get is nothing but it will be a tetrahedron. I don't know how I'll draw it, but I'll just draw like this. The tetrahedron bound by 4 planes. the xy, yz planes, and by this plane that we have. So it will be something like this, and these are origin actually. I have rotated the tetrahedron to give you the feel of how this solid looks like. These are origin, and these three are, if I call it P, Q, R, these points, P, Q, R, something like this. Are you guys following what I'm trying to explain?
Yes, sir.
Okay, so our aim is now to find this triple integral over this volume, the solid D, which is the tetrahedron. So let's see how we do this. So x plus y, dx, dy, dz. So I'll call it D. Well, not D, maybe I'll call it solid S. So now if you look at this tetrahedron, like look at this, I've just drawn the part of the plane that is of interest to us. I've not drawn the whole plane. Notice that the limits of x are given by, see, x is non-negative, right? So the limits of x will be at least greater than or equal to 0. And notice that the values of x will be considered along this x-axis. Look at this x-axis. Look at this x-axis. So x will be non-negative, so it will lie on a positive side. And the value of x will take only up till the value determined by this plane. Is it clear? The upper limit of the values of x will be determined by this plane. Is it clear? Okay, look at the diagram again, the picture again. This is our solid, these are plane, and consider the planes x, y, y, z, z planes. They form a tetrahedron. The limits of x are, I mean, let's look at the plane and see at the diagram and see what the limits of x will be. X is greater than or equal to 0 because that is given in our question itself. The x, y, z are non-negative. X is greater than or equal to 0, right? So x is non-negative. And what is the upper limit of x? If you notice at the figure, you will find that the upper limit of x is like bound by this plane. Guys, you notice this? It can't go
Yes.
beyond this plane. It can't go beyond this plane, right?
Yes, sir.
So what is the plane? The plane was x plus y plus z equal to 1. X plus y plus z equal to 1. So if you write x as a function of y and z, it will be 1 minus y minus z. So these are upper limit of the value of x. So these are upper limit of the value of x, given by 1 minus y minus z. So x goes from 0 to 1 minus y minus z. Column. Write it a little bit far apart because there will be some. So x goes from 0 to 1 minus y minus z, given by this expression, because x couldn't take values beyond that is limited by this plane. And this plane has equation x plus y plus z equal to 1, and at most x can take this value, 1 minus y minus z. I've done this because I've taken x to be our inner integral, the first one. The second one will be dy, and our aim is now to cover the entire tetrahedron given in this diagram, this tetrahedron. So let's take a look at what the limits of y will be. Notice again that y can take positive values only because that is given in our question. X, y, z are non-negative, so y should be greater than or equal to 0. So the lower limit of y will be again 0. Notice again that y can take values like this, greater than or equal to 0, but it can't go on taking it forever, right? Because the tetrahedron should have some upper limit. There is some bound on the value of y. Notice that the value of y is restricted by this particular line of the tetrahedron. Do you notice it, guys?
Yes, sir.
Now, what is the equation of that line? This line has intercepts 1 on the y-axis and 1 on the z-axis, right?
Yes,
So
yes,
this
sir.
line has equation y plus z equal to 1. So the upper limit of the value of y is 1 minus z. Is it clear? So y goes from 0 up to 1 minus z. So dy limit is 0 and 1 minus z. So this is the upper limit of x, the upper limit of y. And dz, z goes from 0 to 1. Because that is our, z equal to 0 means the xy plane, and z equal to 1 means the plane which is something like this, parallel to the xy plane. And of course, the outer integrals should have constants as their limits. Otherwise, we won't get any finite definitive value if the limits are not constants. Is it clear now why we took 0 and 1? Because that is itself given in our equation. X, Y, Z, the values, this one, the values lie between 0 and 1. So Z is between 0 and 1. Is it clear?
Yes, sir.
Okay. So this is our formulation of this limits for this triple integral. Okay. And once we, so the maybe the tough part is only this formulation of limits. Once we know how to formulate these limits, you can easily compute the triple integral. It's very easy now. Then the answer will be, I think, I did it, and the answer comes out to be 1 by 12. Okay, so this is our, in the question it was given, I. This is the value of I. This is I equal to this. So this should be the solid as solid. This is I. So the value of I is 1 by 12. They ask us to compute what is the value of 84 times of I. Right? Look at the question. Then 84 times of I is equal to what? So 84I is nothing but 84 into 1 by 12, it is 7. So the answer is 7. Is it clear, guys, how we did this problem?
Yes, sir.
Okay. So the only tricky part is how you formulate, how you set the limits of this triple integral. So that is the only thing you have to be, careful about, because sometimes you might put wrong limits in these places, and they will give you a wrong answer. So if you practice such problems, maybe you'll get a feel of how these integrations are done. So next problem, change of variables in double and triple integrals. So that is where the Jacobians come in. Suppose we have a double integral of fx with respect to dx dy over some area A, and you want to change the variables. Suppose x, you change it into x is a function of u and v, y you change into y as a function of u and v. Then how does this change of variable affect the double integral, right? Sometimes we do a change of variables because we want to make our lives easier by making the double integral easy. That is why we make a change in variable. So assume that suppose you come at a problem where you are asked to compute this double integral, but it is hard to compute it as a function of x and y. In the variables x and y, it is hard for you to do it. Then what you do is you might be able to transform that problem into another variables. Like you might be able to set x as a function of u and v and y as a function of u and v appropriately. Like that should be a very judicious choice of variables. Again, you should be careful about what variables you choose and how you choose it. Then what we do is, since we have chosen x as a function of x, u and v, y as a function of u and v, we find out the Jacobian of that with respect to the variables u and v. So x, we find out del x del u, del x del v, del y del u, del y del v, and take the determinant of that. It's a Jacobian, right? So ignore this note for a bit. I'll come to this note later on. After you take the Jacobian, come to this step. This double integral that we started off with, this double integral here, this double integral, It will be exactly, see, the function x and y will be a function of u and v now, because you have changed it into u and v variables, right? So that, and instead of dx dy, you bring the absolute value of the Jacobian that you computed. This is our Jacobian. Take the absolute value of that, bring here, and du dv. Now, when you did with respect to x and y, you were computing the double integral over this area A. Now, when you change it into the variable uv, the area might change. Okay, the limits will change, and I have written x bar. Is it clear? That is how we do change of variables in double integral. We do a similar thing too, when we do triple integrals, but I haven't found any question in the exams where there are triple integrals and change of variables. So I'm just doing this one. Are you guys following what I'm trying to say? We'll do problems too. Maybe you'll understand more when you do the problems. Is it clear?
Yes, sir.
Okay, so I'll just give a brief idea of what it means geometrically. So suppose these are your UV plane, right? UV plane, and these are XY plane. The transformation that we had was x as a function of u and v, y as a function of u and v. So this du dv, see, so we have a certain relation between this dx dy and Jacobian absolute value du dv. So in the UV plane, take any infinite single element du dv. So this is area du dv. By this transformation, it will give rise to x as a function, like in the xy plane, it will give rise to some unit element, like infinite single element, whose area is dx dy, and that is exactly equal to the absolute value of the Jacobian times of du dv. And that might be a distortion in shape. If it was a rectangle or a square here, the shape might be distorted depending on what change of variables that we took here. Okay, that is our geometrical interpretation. I'll not go deep into this because this is our problem solving session. So let's try this problem. It was asked in GATE 2018 in mathematics. Let D denote the closed unit disk centered at the origin and radius 2. Then the double integral of this is what? So these are D, closed unit disk. These are D of radius 2. And we want to compute this double integral. So we have been doing this problem tacitly. We are given a disk and we want to compute the double integral of this over the entire disk D. Because there are expressions like x squared plus y squared, and the disk is a perfect, nice disk centered at the origin. I can take the change of variable x equal to r cos theta, y equal to r sin theta, the polar coordinates exactly. Now, when we do that, I ask you to compute this Jacobian, right? So we usually do this, we find this Jacobian. So I'll just find out what del x del r in del x del r. So from, see, it will be r theta coordinates and x theta coordinates. So let's compute del x del r. It will be cos theta, and del x del theta will be minus r sin theta. Del y del r is sin theta. Del y del theta is r cos theta. So the Jacobian is determinant of these values. Cos theta minus r sin theta, r cos theta. So this you'll get to be r cos square theta plus sin square theta will be r. So the absolute value of the Jacobian is just r, because r is all positive, non-negatively, right? Is r. So dx dy is nothing but the Jacobian dr d theta. The absolute value of the Jacobian is r. That is what I kept telling you repeatedly why this R comes out. It comes from this Jacobian, which we obtain by change of variables. Okay, so when you do this double integral will now become double integral of e power minus r squared into r minus r squared dr d theta. Theta lies 0 and 1, I think. Radius 2. So theta lies between 0 and 2 pi. R lies between 0 and 2. You can easily compute this double integral. Right? The answer will be, I think, pi 1 minus e to the power minus 4. Pi 1 minus e to the power minus 4. Option A. Guys, are you following?
Yes, sir.
Okay, let's do this next problem. It was in Gem 22 Maths. We are given an open rectangle G given by this in the xy plane. S lies t plane. So these are x-axis, t-axis, and S lies between 0 and 1. T lies between 0 and 1. And we are given a certain transformation T given by T of S. These are transformation T. T of ST is, look at the question. T of S is pi s 1 minus t by 2, comma pi 1 minus s divided by 2. For ST belong to G. This origin G. We are asked to find out what the area of the image TZ is. So these are G, and by the transformation T given in the question, we transform it into a certain region TZ, and I'll call it XY plane. Like I just take X. It could take UV plane, whatever plane that you want to take. I'm just taking it XY plane. Okay, the TZ lies in the XY plane for our, to make things easy. Then the area of TZ is nothing but dx dy. You compute it over the entire region TZ, right? This is our area of the image TZ. Now let's look at the change of variables. TST was given to be TST was pi s 1 minus t by 2 pi 1 minus s by 2. So the change of variable that I'm taking is s x equal to this one, pi s 1 minus t by 2, y equal to this one. This is y, this is x. This is the change of variable that I'm taking, 1 minus s by 2. Then after this change of variable, we find out the Jacobian, right? Because dx dy will be, so let's find out what del x del x del s is. It will be pi by 2 1 minus t. Del x del t will be minus pi s by 2. Del y del s, because x is now a function of s and t, so we are finding the partial derivatives with respect to s and t, with respect to s, with respect to t. Y is again a function of s and t. Y is a function of s and t. So del y del s, it will be minus pi by 2, I think. Del y del t will be 0. So the Jacobian is the determinant of pi by 2 1 minus t 0 minus pi s by 2 minus pi by 2. That is nothing but minus pi square by 4s. That is our Jacobian. So these are Jacobian, and the area of the image now is the absolute value of the Jacobian and in the variables ds dt. So the limits of s are 0 to 1, t is from 0 to 1, right? That is our square given to us. S lies between 0 to 1. Look at the question. S lies between 0 and 1. T lies between 0 and 1. Look at the question. So the absolute value of the Jacobian is nothing but, you remove the minus, so you will pi square by 4s right? So if you put it here, pi square by 4 will come out as ds dt. S lies from 0 to 1, t lies from 0 to 1. The answer will be pi square. I think it will be pi. The answer is pi square by 8. The third option. You can check easily if you do this integral. So this kind of question is was asked in gate 2. Is it clear now how we found out the area of this image?
Yes, sir.
Okay, so that is how we use the change of variables in Jacobian to find out the area of this image. Now this next problem, yeah. So let R, this was asked in GATE 2019 maths. Let R be the region bounded by the curves, this and this. The value of this double integral is what? So look at the curves given to you. The region is given by, like, is bound between the curves y equal to x squared, y equal to 4x squared, xy equal to 1, xy equal to 5. And you're asked to find out this double integral. Right? What is this double integral? Over this, this is the region A. So you're asked to find out the double integral over this region A. So there is no easy way of doing this double integral, right? It's not as simple as this double integral that we have here. If you look, this was very pretty simple. Everything was simple, but now it's not simple. So let's go about trying to change the coordinates, trying to change the variables. So see, there's a certain pattern here. Y equal to x squared, you can write it as y by x squared equal to 1. Y by x squared equal to 1. And y equal to 4x squared, you can write as y by x squared equal to 4. Here xy equal to 1 and 5. 1 and xy equal to 5. Right? So we can choose our variables to be something like this. U to be y by x squared. We can choose our variables u to be y by x squared. V to be our variable xy. Right? So see, usually what was done here was, the theory was that when you use such substitution, x is a function of uv, y is a function of uv, you find out del x del u, del x del v, like this. But now it's not like this. It's slightly the opposite. There are so many problems that I chose, but okay. U as a function of xy, v as a function of x, it's like reverse way. So what we do is, let's just find the Jacobian of u and v with respect to x and y. So del u, del v, del x, del u, del y. Find the Jacobian, del u, del v, del x. Sorry. Del v, del x, del v, del y. Right? Find the Jacobian. And we set j, right? But now instead of j, I'll set this to be equal to 1 by j. That was my note, which I told you to skip. If the Jacobian is hard to compute, like if it is something like this, where you have to write, see, this was our substitution, right? U, v to be like this. You have to, in the, like, if you do it the way that the theory exactly is, then you first find x as a function of uv, y is a function of uv. But that is not so in our problem, right? Because while doing that and while computing all the partial derivatives, it will be hard. Like, it will be time consuming for you. So instead of that, just compute as it is. Jacobian of u and v with respect to x and y. And instead of setting it to be, find a determinant, and instead of setting it to be j, I'll just set it to be 1 by j, the reciprocal. Do that, and from here, you find out what the absolute value of j is. Okay, you can do these things, and the absolute j turns out to be 1 by 3u. I've done it because I was asked to prepare for this, so I've done all these things, and I found this to be this. I urge you to check it and find it out. And so this double integral dy dx over the region A will be exactly equal to, in these variables, y squared by x. Y squared by x, if you you can check that y squared by x is equal to uv. Okay, So y squared by x will be uv, and the absolute value of Jacobian is 1 by 3u, so this one, and here du dv. So u limits are, this we have set to be u, so between 1 and 4, right? The values of u are between 1 and 4. The limits of v are between, I think it is, this we set to be v, xy was set to be v, so the limits of v are between 1 and 5. 1 and 5, and this is very easy to compute. The answer is 12, I think. Is it clear now, guys? Or am I, I'm being fast because like we are approaching the end of this session, and there's still one topic that I want to cover at least. Is it clear?
Yes, sir.
Okay, so just mind, like when you go to the video, just like watch this part, what I'm trying to explain you. Like this one, this is also important. When you find it hard to compute the Jacobian like this, find the Jacobian as it is, del u del x, like the reciprocal of the ulta, thing, and then set the determinant to be 1 by j, and find out the absolute value of the Jacobian, and then proceed as usual that I've told you here. Okay, so that was what we used in this problem. And the last topic, yeah, this is the,
Krishna, hello.
yes, sir.
We are almost the end of the time. Shall we postpone that to the next session?
It's a very small one. Maybe I can finish it in 5 minutes. So
Okay, then you can. Okay.
yes. So this is the last topic, change of order of integration. That is very important because questions are asked. As for example, this question, I'll tell you how this is done. So look at this question. You are asked to find this double integral sine y dy dx, and see y comes up here first, right? The inner integral. So y limits are, look at this question in the image here, x and pi by 2, and the limits of x are 0 and pi by 2. So what is the order, what do you mean by change of order of integration? So by that I mean that like if you integrate this, you have to integrate with respect to y first, and then after that you have to integrate with respect to x, right? So y first and then x. Now changing the order means doing the reverse of this, x first and y. Now there is a lot of benefit of lots of advantage of doing this change of order. Why? Because if you look at this function sine y by y, there is no easy way of doing this integration with respect to y, right? There is no easy way of integrating something like this with respect to y. So it's like if we change the order of this integration, it will be like very easy for us. As for example, take a look at how we can do this. So to do such integrations, we first, it is always a good idea to know what the area is over which we are trying to integrate the whole function. So y lies between x and pi by 2. So y equal to x is this line, right? Y equal to x is this line. This y equal to x. Now y equal to pi by 2, I'll maybe set this line. This is y equal to pi by 2. So y lies between x and pi by 2. So there's a vertical, traversal. And x lies between 0 and pi by 2. So x lies between 0 and pi by 2. This is also pi by 2. So first we are going towards along y, and then we're going along x. So when we do this, we are integrating over this like area. Another way of doing this is by traversing along x. So along x first, and then along y. So if you travel along x, then this was our line y to x, right? If you travel along x, then x lies between 0 and y, right? And y lies between 0 and pi by 2. See, it starts from here, so y lies between 0 and pi by 2. X lies between 0 and y lies between 0 and pi by 2. So the same thing, if I change the order, so this whole integral, if I change the order of integration, then sine y by y I'll integrate with respect to x first. So x lies between 0 and y. And y lies between 0 and pi by 2. So the advantage is very much evident now. So if we integrate with respect to x, this is a function of y, so this will be treated as a constant. So y lies between 0 and pi by 2. So sine y, so y into, if we do this double integral now, it will be y dy. So y cancel. So that was this factor was the problem, right? While integrating this function, this was a problem for us. That problem disappears now. So it will be sine y dy over y equals 0 and pi by 2. I think this is 1. Yeah, so this is very much how we do change the order and why we do it. The same thing with this problem. This is our region, and I urge you to try it. And the answer is k equal to 1 by 4, and this is 0.25. If you follow that, then you can do this very easily. And this one also, it's very easy. Do this, and maybe the answer is, I think, 1 by 2 pi. The answer is 1 by 2 pi. Yeah, sir, this I wanted to cover these problems, but I don't think that we have time. These were some problems that I wanted to cover, miscellaneous problems.
Yeah, that we can postpone to the next session, I think, because
Yes, yeah.
we're just out of the time.
Yeah.
Now you may please turn off the presentation and keep your video on. We can move to a interactive session.
Okay, sir.
Thank you, Krishna, for this nice session with a good collection of problems. You have explained only the necessary theory in between and explained many important problems from the previous question papers. I'm sure that this session will be really very helpful in the preparations of our students. So, dear students, now it is your time. You may please share your feedback, or if you have any queries, you can ask it now. Please turn off the presentation.
Sir?
You can turn off the presentation, I think. The presentation is...
Okay, the screen sharing, right?
Yeah, yes.
This is all new to me. I'm trying it.
Yeah, it's okay.
Okay. Is it off now, sir?
Yeah, but your video is not available. Please keep the video. Yes, right. Okay, dear participants, please feel free to share your feedback. Yes.
Hi, sir. I'm Shreya.
Yeah.
Hi.
Thank you for this class. It was really informative. The concepts and problems you explained it really well. It was easy to understand. Thank you, sir, for your time. And thank you, Vinod, sir, for arranging this class for us.
Thank you so much for attending. Thank you so much.
Yeah.
Hi, sir. I am Parvati from St. Teresa's College, Kerala. Thank you for organizing. Thank you for giving such a wonderful session. The session was really helpful. We are expecting more of such sessions. And special thanks to Vinod sir for organizing this session. Thank you.
Thank you so much. Thank you.
Hello, sir.
I am Krishna from Government Victoria College, Kerala. Your session is very informative and so amazing classes. And special thanks to Vinod sir to organize this session. And thank you, sir.
Thank you so much. Thank you.
Yeah, it's Karthik.
Good afternoon, sir. It was indeed a wonderful session with you today. And all those hard topics of the multivariate calculus were explained with such grace and dignity. I would like to thank both Krishna sir and Vinod sir for organizing such a wonderful session. Thank you, sir.
Thank you.
Hi, sir.
Yes.
I'm
Yeah.
Nisu from Govt Victoria College, Kerala, sir. Thank you for spending your Sunday with us, sir. We are expecting your pending classes too. Thank you, sir.
Thank you so much. Yeah, we will do more sessions too, because there are some. I didn't cover all because it's a big part, and I asked for like, yeah, I'll say things. Yeah.
Okay, sir. Thank you.
Okay. Thank you, Neetu. Yes. Yes, others.
Hi sir, I'm Ananda from St. College Ernakulam, Kerala. So the class was very useful. It was like rewinding some of the theories and problems from previous semesters, and it was very useful. Thank you, sir, for the session, and thank you, Vinod, sir, for arranging such a beautiful
Thank you.
session.
Thank you so much.
Yes, Shikha, you can speak.
Good afternoon, sir. My name is Shikha, and I have completed my integrated M.Sc in Mathematics and Computing from Birla Institute of Technology, Misra, and I'm from Jharkhand. Sir, your session was really helpful, and the collection of questions was it was a good collection. It has given a very thorough practice for us, and it's very helpful. Thank you, sir, for such a good sessions, and hoping for more such sessions from your side. Thank you, Vinod, sir, for organizing such sessions.
Thank you. Thank you. Yeah.
Hello, sir.
Yeah, Praveen.
Hi.
Yes, Praveen.
Sir, in the beginning, you had said that you had a passion to teach, and I must say that that was very evident throughout the entire class. So, thank you for the great session. Sir, I have a query. Apart from hard work, can you give any smart work tips?
Yeah, when it comes to cracking exams like GATE, the thing is, like you have to know how your mind works and like what your weaknesses are and what your strengths are, right? So, like first, maybe I'll suggest that you first find out where your weaknesses are, where you are like loose on your concepts, where you don't have, you're not very strong, and work on that first. Try to overcome your weakness first. That is the first thing that I did when I was preparing for my GATE exam. I tried to identify my weakness and I tried to cover that. I tried to make myself strong in those things. And once I did that, gradually your confidence will be like going up and up. You'll feel that you are covering your concepts. You are like getting clearer and all. Yeah, that is what I suggest you to do. First, find your weakness and work on that. And after that, see, lots of people, what they do is they just try to, give the past, like, there's something like, I've forgotten the name of it. It's like, exam series and all. For some people, the exam series works. For some people, it doesn't work, right? As for example, it didn't work for me. So before GATE exam, I didn't give any exam series. I just worked on myself. I worked on building my confidence and all those things. I didn't give a single exam series because I tried that. And when I didn't perform well in the exam series because of certain reasons, then you'll find that your confidence is like suddenly low, and that is very harmful when you are preparing for an exam. So if the exam series and all those things works for you, go ahead. It's very good. But if you find that it is not working for you, then it's better, I think, to not go into all those things and instead work on your own. Like that is what I did, right? So it worked out for me. And another thing is, often you're advised that when you're attempting a question, try to complete it within 2 minutes or 1 minute. I think that is like not a very good idea because if you are asked to do like that in a very time bound manner, you're like you are constantly stressing yourself out. Like there'll be stress that I have to do it in 2 minutes, I have to do it in 1 minute. So that is not a very good idea because when you sit in the exam hall, you'll find that some questions you can attempt in a very short time, like within 1 minute, and some might take a little long time, 3 minutes. So, and moreover, it's not possible for us to try each and every question, right? So, questions are set in such a way that we can attempt some of them, and the others we have to leave it. So it's better to focus on two things. First is how clearly you think when you think a problem. Try to think clearly. And the second thing is try to think deeply. So two things, clarity of thought and depth of thought. Try to focus on these two when you study. So I think that should help you a lot. And don't worry too much about the time bound factor. Like in 1 minute you have to complete it, in 2 minutes you have to complete it. No, that doesn't work because some problem might take a short time, some might take 2, 3, or 4 minutes. And overall, when you do it in the exam, everything will be averaged out. And if you can think perfectly, like not perfectly well, but if you think well enough in the exam, if you can think clearly and deeply well enough, then obviously your exam will be good. So that is what I want to say. So like, I just want to clear out the various misconceptions that people have about exams, like exam series or this peso ka fanda and all those things. I want to clear all this. That's what I want to say to you. Just work on your confidence, work on your weakness, try to try to make strong where your weaknesses are. That is what I suggest to you.
Okay. Yes.
Hello, sir.
Yeah.
My name is Sarah. The session was very good, and especially the graphs. It helped us to understand the question a lot more clear. And thank you, Vinod sir. Thank you for organizing the session, and thank you, sir. Thank you so much.
Thank you so much for it.
So,
Yes,
I'm Shama from Aspirants University, Bangalore. So this topic is little difficult for me, but I was able to follow most of the things. Your explanation was like easy to follow. Thank you so much for the class, sir. Thank you, Vinod sir.
Thank you so much.
Thank you, Shama. Yes, Shikha. Yeah.
Yes, sir. Sir, I wanted to know more about your field you are working on and what motivated you to choose this field.
Right now, I'm at IIT Kanpur. I took M.Tech for some reason. Like, I thought I like like astronomy and all those things. So maybe I thought it's like only for 2 years and all those things. So I decided to apply here and I got it. After coming here and after attending all the classes, I find that like, this is not really my taste at the moment because there's a lot of applied maths going on, and actually my taste is in pure maths like analysis, topology, and all those things. That is where my interest lie actually. So I've decided to drop out, and I'm still at IIT Kanpur so far, and I'm thinking what my options are. Either I'll go for PhD, or if not, I'll try to be teacher somewhere. That's what my aim is at the moment. If I go for research, I would like to go into geometry maybe, topology and technical theory and all those things, complex geometry and all those things. That is what I'm interested in. If you are asking for my interest.
Okay, sir. Nice to meet you.
Welcome.
Thank you.
Welcome.
Any others? If any of you would like to share any comment, you can make it now. Otherwise, we will wind up here. So thank you, Krishna, for being with us. And it will be better if you can share the PDF of your questions along with the explanation. If it's possible, please try to share it as a PDF. We can share it with the recorded video of our lecture.
Okay, sir. Maybe I'll write the solutions and everything, and maybe I'll send it to you, sir. And maybe I think, sir, is that better?
Okay. Yeah, you please share that PDF with me. I will try to share it with the students. It will be certainly very helpful for them.
Okay, sir.
So thank you everyone. And okay, let us wind up here. Bye.
Bye, everyone.
Yeah.